The second law of thermodynamics for a control value. The second law of thermodynamics can be applied to a control volume by procedures similar to that used in chapter 6 for a first law, where the first law was developed for a control volume. We start with the second law expressed as a change of the entropy for a control mass in a rate form. The entropy change on control mass on dt equals to the summation of q dot on t plus s dot generation, to which we now will add the contribution from the mass flow rate in and out of the control value. A simple example of such a situation is illustrated in this picture. This picture provides an example for control value. The flow of mass does carry an amount of entropy S, as shown in the picture here. The flow of mass carry an amount of entropy S. But it does not give rise to any other contribution. As an process may take place in the flow, entropy can be generated, but this is attributed to the space if it belongs to, for example, inside or outside the control volume. The balance of entropy and as an equation then state that the rate of change in total entropy inside the control volume the rate of total entropy inside control volume is equals to the net sum of fluxes across the control surface. The control plus the generation rate. So we can write rate of change plus in minus out plus generation. Or we can write this relation, rate of change, D is control value on dt, the summation of inlet, n dot I is I minus n dot E exit SE plus S dot generation. These fluxes are mass flow rates carrying a level of entropy and the rate of heat transfer that takes place at a certain temperature. The accumulation and generation terms cover the total control volume and expressed in the lumped that we have this relation. M dot control volume S MASA plus MBSB MCS S dot generation rho S dot generation TV plus S dot generation equals to total of S dot generation, for example, A if the control volume has several different accumulation units with different fluid states and processes occurring in them, we may have to sum the various contributions over the different domains. If the heat transfer is distributed over the surface, then an integral has to be done over the total surface area using the local temperature and rate of heat transfer per unit area. If the heat transfer is distributed over the control surface, then an integral has to be done and integral has to be done over the total surface area using the local temperature and rate of heat transfer per unit area. Q dot, we can write the control value on temperature These distributed cases typically require a much more detailed analysis, which is beyond the scope of the current presentation of the second law. The generation terms from a summation of individual positive internal irreversibility entropy generation terms from a summation of individual positive individual positive internal irreversibility entropy generation term. And equality is often written as ds on dt plus sigma control volume on T. Now the equality applies to internally reversible and the inequality to internally irreversible. The form of the second law is general such that the particular case results in a form that is a subset of the form. Example of various classes of problems are illustrated in the following sections. If there is no mass flow into or out of the control volume, it is simplified to a control mass and to the equation for the total entropy reversed back to a simpler relation. Since that version of the second law has been covered in the previous chapter, here we will consider the remaining cases that were done for the first law also in chapter 6. The next section is the steady state process and the transient process for a control value.